Hello everyone, today we are going to do 4.5 exponential growth and decay modeling data. Basically this is just applying what you have been learning with logs to like word problem type situations. So actually this is just like the PERT equation. We're just going to change a little bit to A equals A sub 0 e to the kt. And you can use this for growth and decay. A would be your amount in the end. And A sub 0 would be your initial amount, or the amount in the beginning. And then E is E. K is your constant. Or the variable of growth, I guess. Or constant for growth. Okay, if K is positive, it's growing. Oops. Not growth, decay, growth or decay. Alright, if K is positive, K is greater than 0, it's growing. And if K is less than 0 or it's negative, it's something that's decaying or dying off, something, there's becoming less of it, whatever the thing may be. And then T is your time. Alright, so first, for example, or checkpoint 1, we're going to look at population growth. Alright, so this one says in 2000, the population of Africa, so in 2000, the population of Africa was 807 million people. And by 2011, it had grown to 1,052 million, which you'd really say 1 billion, but 1 billion, 1.052 million, I guess. Okay, so for part A, it says use the exponential growth model, in which t is the number of years after 2000 to find the exponential growth function that models the data. So we're going to start with A equals A sub 0 e to the kt. So in 2000, that's our year 0. So in 11 years, it grew to that. So our ending is 1052. The beginning is 807. We have e to the k, and then we know this is times 11 years. So what we're going to be doing here is finding k. We're going to use this information to figure out what k is. So first I'm going to divide by that. It's not going to be a nice number. Like if we were to divide 1052 divide by 807, it's not a nice number. It'd be a number we'd have to round. So I'm just going to actually leave it as a fraction. 1052 over 807 equals e, and then I'm going to change it to 11k. But we need to solve for k, so I'm going to take the natural log of both sides. So natural log of 1052 over 807 equals 11k. and then we just divide by 11. So the natural log of 1052 divided by 807 all over 11 equals k. Now I'm going to approximate k. So k is approximately, let's see, natural log of 1052 divided by 807, and then divide that answer by 11. So k is about 0.024. Okay, but that's not our answer. We're actually looking for the model. So the model would be with that plugged in. So it would be A equals, our A sub 0 will always be 807 million. E to the 0.024 t. Okay, that's the model for the population of Africa. For B, it says, by which year will Africa's population reach 2,000 million? Excuse me, or 2 billion. Okay, so to solve that, we're going to use the equation from part A. That would be our A. So 2,000 equaling 807 e to the 0.024 t. And we're going to actually just solve it the same way we had done the one before. So divide by 807 equals e to the 0.024 t. To get that t down, we're going to take the natural log of both sides. Which natural log of that is just the 0.024 t, because the natural log of e is 1. And then we just divide by 0.024. And we can see approximately what t is. So natural log of 2,000 divided by 807 and divide by 0.024. We get about, let's say, 38 years. So remember, this is how many years, that's like what t is 38 years after the year 2000. So by what year will it reach 2,000 million or 2 billion people? It would be the year 2038, because we're going at years after 2000. So that would answer that question. All right, and then checkpoint 2 is going to be a half-life problem. Okay, for this one, it says strontium-90 is a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have a measurable amount of strontium-90 in our bones. The half-life of strontium-90 is 28 years. Meaning that after 28 years, a given amount of the substance will have decayed to half the original amount. Find the exponential decay model for strontium-90. Alright, so All right, so we're using the same thing we just used in checkpoint 1. We're using a equals a sub 0, e to the kt. Okay, now the a and the a sub 0 can be whatever you want it to be. It just needs to be that you end with half of what you begin with. So if we begin with 2, we end with 1. I think that's the easiest way to do it. And then e, we don't know k, but we know that it takes 28 years to get to half. So you divide by the 2, you get a half, or let's do 0.5, equals e to the 28k. Take the natural log of both sides. So the natural log of 1/2 equals 28k. Divide by 28. So k is approximately natural log of 0.5 divided by 28. And so k is negative since it's decaying. So let's say negative 0.025. Okay, so our actual model, remember that's just the k, that's not the actual model. The actual model would be a equals a sub 0 e to the negative 0.025 times your amount of time. Now part B, it says suppose there is a nuclear accident and releases 60 grams of strontium-90 into the atmosphere. How long will it take for strontium-90 to decay to 10 grams? Okay, so we're doing 60 grams to 10 grams. And we want to know how long will it take. So we're going to be finding T. So we're going to use our model we just made in part A. And we know our beginning and our end. So we're having 60 turn into 10. So the end would be 10. The beginning is 60. So to solve it, divide by 60 first, which that is 1/6. We're going to take the natural log of, you can call it 1/6, you don't have to call it 10 over 60. And then the natural log of e to the negative 0.025t. So natural log of 1/6 equals negative 0.025t, because the natural log of e is 1. And then divide by that. So natural log of 1/6 divide by negative 0.025 equals our t. So then we can plug that into our calculator and get an approximate for t. So natural log of 1 divided by 6 divided by negative 0.025, and we get about 72 years. And this one's not a by which year problem, so that's your answer. All right, checkpoint 3 has to do with a logarithmic growth model. And really with this, you just need to know how to enter it into your calculator. And you just need to be careful when you do that. You don't have to be able to actually make this model. And this is for when growth has a ceiling. Okay, so the generic formula is A equals C over 1 plus A e to the negative bt. And what this is, it's a model that represents growth that has a ceiling. So if something grows, but it's never going to grow above that, like the height of people. Like there's a certain height that people will just never get above. Maybe, I don't know, who knows. But that's what we're approaching. That amount is actually C. Okay, and that's your limiting size. That's what that's called. Or I didn't mean 6, I meant C. Sorry, the amount on the top. That's as big as you're going to get. Alright, so for checkpoint 3, we're going to look at a logistic growth model. We're given f of t equals 0.8 divided by 1 plus e to the negative 0.2t. And it says, in a learning theory project, psychologists discovered that this function is a model for describing the proportion of correct responses f of t after t learning trials. A, find the proportion of correct responses prior to learning trials taking place. So prior to when learning trials taking place, that's when t is 0. So we're going to plug 0 into our formula. So f of 0 would be 0.8 divided by 1 plus e to the negative 0.2 times 0. So that's 0.8 over 1 plus e to the 0, because anything times 0 is 0. Anything to the 0 power is 1, so you have 1 plus 1. 0.8 divided by 2 would be 0.4. So prior to learning trials taking place, 0.4 would be the amount of correct responses that you would expect to get. For B, find the proportion of correct responses after 10 learning trials. So this is when t is 10. So f of 10 would equal 0.8, and you're just plugging it in for t. 1 plus e to the negative 0.2 times 10. So 0.8 over 1 plus e to the negative 2. And then actually you just throw that into your calculator. Very carefully. So 0.8, trying to get where we don't have glare here. So 0.8 divided by parentheses 1 plus, I'm going to go ahead and put this in parentheses too, e to the, I'm just going to throw in negative 2, oops, let that go down, close parenthesis, and you get 0.7, so it's moved up. It's like percentages, 70% correct. When in the beginning it was 4%. So that's after 10 trials, you get 0.7. Then part C asks, what is the limiting size, f of t? Limiting size, f of t, of the proportion of correct responses as they take place. Remember, your limiting size is just your c. So what's the number on top? 0.8. So the top number, or c, is the limiting size. All right, that is it for 4.5. Your chapter 4 test will be on Friday. Have a great day.